Okay, 12, welcome to the next video here for modelling nonlinear relationships. We're looking at exponential functions here today. Now, exponential functions are where the variable is in the exponent. All right, remember our indices, we have a coefficient, a base, and an exponent. Right? If x is up there in the exponent, we have an exponential graph. Right? Think about what happens if I graph. Right? Let's say y equals 2 to the power of x. Right, for various values, x and y, right, little table of values here, right, if x equals, we'll put a negative in there, -1, 0, 1, 2, and a 3, right. Now, first of all, let's have a look at, I'm just going to choose up here, 2 to the power of 2 to the power of 2, 2 to the power of 2 equals 4, 2 to the power of 3 equals 8, 2 to the power of 1 is 2. 2 to the power of 0, can you remember 2 to the power of 0 is always equal to 1. 2 to the power of -1, right, is the same as 1 over 2 is 1/2, right, 0.5. Now what we're going to see here is that this is increasing, goes up by 1, goes up by 2, goes up by 4, the next one is going to go up by 8, and then by 16 and so on. It's increasing at an increasing rate. Or if we work backwards, I'm sort of halving it each time. If I halve that, I'll get a quarter. If I halve that, I'll get an eighth, and so on. So, there's no power that I could raise to make it a negative number. I can make it really small, but I can't make it negative. That means that the graph of this function is always above the x-axis. And as I work my way to the right, it gets really big, in fact quite fast. As I work my way to the left, right, it gets smaller, 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 never gets to 0, never becomes negative. Right, we call that thing we call this thing here an asymptote. Right, the same as for hyperbole. Hyperbole have 2 asymptotes. An exponential function has 1. So the graph of y equals 2 to the x looks like this. Asymptote here goes up, right? Now, it crosses over. Right, there's x, there's y. This is when x equals 0. If x equals 0, y equals 1. Okay, because something to the power of 0 equals 1. Now, should this number be less than 1 but more than 0? Right, if my base is less than 1 and more than 0, think about this table of values, right? It's still going to cross here, right? 1/2 to the power of 0 still equals 1. Still going to cross over here. But a half squared, well, in fact, if x equals 1, then I just get a half. Right, that'll be down here. And a half squared is equal to a quarter. And a half to the power of 3 is an eighth, and so on. I get the asymptote here. Now, 1/2 to the power of, for example, -1 would be 1 divided by a half, which is the same as 1 times 2 equals 2. Now, 1/2 to the power of -2 would be the same as 1 divided by the square of a half, which is a quarter. 1 divided by a quarter, right? How many times can I subtract a quarter from 1? I can subtract it 4 times, okay? So it's the same as 1 times 4. So, if my base is less than 1, but greater than 0, then I have what's called exponential decay. Looks a bit like this. Right, crosses there at 1. Oop, that's a 1. Could be anything. That's a 1. Now, this is exponential growth, exponential decay. We are not going to look at cases, well, we can't have a function if that's a negative number. Right? That doesn't happen. So, exponential growth is where my base is greater than 1, and x is in the exponent up there. Exponential decay, where my base is between 0 and 1, right, where my base is a fraction or a decimal, and again x is in the exponent, exponential decay. Now the curve is, if a is greater than 1, then the curve is always increasing. And the larger the number, the steeper the curve. Right? So if I had something like y equals 3 to the power of x, right? Still cross here at 1, but it would grow up faster here. Because think about 2 squared is 4, but 3 squared is 9, right? 2 to the power of 3 is 8. 3 to the power of 3 is 27. Okay, so it would be much faster. The graph of this one here is always decreasing. The smaller the fraction, the steeper the curve. Okay, so 4 times 2 to the x. Now that's not the same as 8 to the x, right? But nonetheless, we're going to have very fast up here. Now, where's it going to cross here? What's 4 times 2 to the 0? 2 to the 0 equals 1, so I get 4 here. Okay, it's 4 there. Right, 4 times 2 to the x is not the same as 4 times 2 all to the power of x. It's not the same as 8 to the power of x. We get this one here, 0.3 times 3 to the x. Now, this is not decay. Right, this is still a growth. It's still going up like this because it's 3 to the power of x. It's just that it's happening not as quickly. Okay, so what I'm going to get is still this same sort of curve, but this one here is 0.3. Okay, still growth because the base, right, that which is raised to the power of x is still greater than 1. Now, the b value of this changes the value of the y-intercept, right? You can see this number here in front, there's my 4, the 0.3 here. It moves the graph up or down, not in the same way as a plus on the end does. It sort of pivots the graph a little bit. No, maybe that's not the best way to describe it. It changes the steepness of it. That's a good way to understand it, right? Is in a similar way to our other graphs, okay? Now, we'll have a look at these next things here with exponential growth, these applications of this later on, which are really important. But for the time being, in terms of recognizing the graphs, right? Recognizing these graphs, their names and the equations, exponential growth, exponential decay, right? Where x is up the top there as a power. Okay, those are the key things to take from this. Okay, I'll see you in class.